So hi everyone, welcome back. Hi Nir, hi Mike. How was your last two weeks since last time we met?
Hello. It was nice to meet. Sorry, just started talking.
Nice to meet you too, Mike. We love you. We love you.
Yeah. The last 2 weeks, I got to say that I missed our episode, and the only reason we didn't record the last Sunday that I was a bit sick, but now I'm okay and fully ready for the new episode.
Glad to have you back, and good that you're recovered fully. And Nir, how are you?
Good. It was a busy 2 weeks, but
Yeah.
it's Sunday now and it's sunny outside, so let's do it.
Yeah.
Okay, cool. So as promised, today we start with, or we're gonna review the paper, the seminal paper by Shannon, A Mathematical Theory of Communication. It was published in 1949. After reading it, so the whole paper is like 50 or 60 pages, but half of it is the paper and the second half is all the derivation of the theorems. So our plan is to go over the paper itself, which is also quite a heavy task. And I must say that in retrospect, my struggle was with so many concepts, right? So he defines concepts in a really structured way. Starts with, like, in a sense, information, then entropy, etc. But still, like, at some point I'm reading in the middle and I'm like, wait, what's going on here? I need to go back. It was a lot of concepts to think about, and I'll try from my side to make them clear in our presentation. And if we like get stuck, we'll try to understand the concepts again. And I think like it feels as someone's PhD. And Mike, I think you said that's like more in today's terms, it's like a few PhDs. So
Yeah,
tell me your thoughts like after reading it.
I think it was a quite tough paper. I think the first time I encountered this paper, it was about 25 years ago, and then I've read it and I thought, wow, it is a very great. It is a really great paper, and a lot of concepts. Each one of them is explained very clearly. But also difficult in this paper, and why it was difficult for me. Then I reread it a couple of days ago, because we just got used to the modern paper talking about one or maybe two concepts. Here in this paper, there is a multitude of concepts, and although all concepts are very clearly explained, the interplay between these concepts is quite hard, because my brain is just operating in the regime that each paper is just one concept. I'm reading, I understand the concepts. This is okay. In this paper, the situation is totally different. You have about 7 or 8 different concepts, not very trivial concepts, and not only I need to understand each one separately, and you need to understand the interplay between and the synergy between these concepts. So it was not easy. It was tougher than our previous paper, but still, I hope I managed to do it.
And I'm curious, what made you read it in the first time, 20-something years ago?
I don't remember. I love reading papers. Maybe it was not 25 years ago. Maybe it was about 20 years ago when I started working in the communication field. Years before I started to teach the course which Nir studied under my supervision, and this was one of the papers my former boss, Doron Ezri, told me to go over. I think so, because I had zero knowledge in signal processing. I even thought that Fourier transform is some mathematical function without any additional meaning. You know, I was a pure mathematician, so I think the reason was that he recommended me to reading it. I think
Okay,
so.
you read this paper and you got 0 signal processing out of it. No?
Yeah. Not zero, but
Not 0,
but close to this.
small amount of information.
I've got a small amount of information, and not but you need to understand that when I started working in a signal processing field, my knowledge in the information theory was 0 as well, because I never studied this subject in the university. Then I took a couple of courses about it, but then I started working in the field of communication 2005, I think, more or less 20 years ago. I have 0 knowledge in signal processing and in information theory as well, because I did my PhD in stochastic processes, probability, some statistics, but not information theory.
Cool.
This was my long one.
No, that's a cool history of the paper. I guess, Nir, you also have some history with the paper as someone who's into estimation and electrical engineering.
Yes, for sure. Yes, I actually, in my graduate studies, I took a course that is titled Information Theory. And this course, now that I read the paper, I mean, they mentioned Shannon, obviously, not a great deal. They mentioned the name, okay? But you know how it is in a graduate study. You don't have a lot of time to read outside the assignments that you get and the things that you're doing in your research. So I didn't read this paper before. Actually, I haven't read it, but everything that is described, almost everything that is described in this paper is actually the content of the course that I took, which is, it's like a course. Think about a paper. Try to imagine, maybe the listeners try to imagine a paper that is substantial enough to facilitate the full graduate course over a semester. This is this paper. And by the way, Shannon was an electrical engineer and a mathematician. So he had 2 PhDs, I think, or 2 master's degrees, or something like that.
Interesting.
So it's an intersection between mathematics and engineering here, because he's talking about signal to noise ratio and all the thing, and like communication. Obviously, it's engineering, communication theory, I mean, but the theorems are highly mathematical, right? As we will see soon. So
yeah.
I think
So
his intersection with this. Sorry, go ahead, then.
I wanted to say that if we're trying to go over a paper that takes a whole course to learn, that's quite a hefty task.
Yeah, but you know how it is. In the course, they present the theorem, they prove it to you. You know how electrical engineering goes. We're not going to do that in this talk, obviously. So
yeah. Hopefully we're going to prove any theorem.
No.
Otherwise, it will take ages. This episode.
But hopefully we'll get the motivation behind the concepts. I think that would be
Yes.
great help.
Yeah, by the way,
yeah.
small remark, the author of our previous paper was a doctor, right?
MD, yeah.
Integration.
Yes.
He was a doctor and a mathematician, and here we have the same case.
Yeah, this is an electrical engineering.
Yeah,
PhD,
I mean the same case that he had 2 professions.
Yeah. The same variety of topics.
Yes.
You know, when I think about it, like 100 years ago, 200 years ago, Gauss, Cauchy, all of these great mathematicians, they were always doing something, building something, like engineering. They were, for example, Gauss, he devised the linear regression or least squares estimation, a nonlinear least squares estimation because he looked at the stars and the planets going around. There was no pure mathematics back then, I think, in the sense that we have today.
Yeah. Interesting.
So I'll start with reading the important parts that convey the main message. So it's the second paragraph, but here he talks about what he's trying to do. So he says the fundamental problem of communication is that of reproducing at one point either exactly or approximately a message selected at another point. Frequently, the messages have meaning. That is, they refer to or are correlated according to some system with certain physical or conceptual entities. These semantic aspects of communication are irrelevant to the engineering problem. The significant aspect is that the actual message is one selected from a set of possible messages. The system must be designed to operate for each possible selection, not just the one which will actually be chosen, since this is unknown at the time of the design. So that was interesting because he already says, there's meaning to messages, but we engineers, we don't care about meaning.
Yeah.
We're gonna do engineering. Reminds me of today, AI ethics. I don't care about ethics. I wanna train ML models. I don't know if it's the same. A good analogy, but I was reminded of that while reading.
Okay.
And then he continues.
Yeah.
That's also important here. He says, if the number of messages in the set is finite, then the number or any monotonic function of this number can be regarded as a measure of the information produced when one message is chosen from the set. Okay, so he's already introducing the concept of information. All choices being equally likely. As was pointed out by Hartley, the most natural choice is the logarithmic function. Although this definition must be generalized considerably when we consider the influence of the statistics of the message, and when we have a continuous range of messages, we will, in all cases, use an essentially logarithmic measure. Okay, so he's already introducing, okay, guys, you're gonna see a lot of logarithms.
Yeah.
And then he says, okay, why? And this was interesting for me. He says the logarithmic measure is more convenient for various reasons. So he's trying to convince us why logarithm is a good choice. He says it's practically more useful. Parameters of engineering importance such as time, bandwidth, number of relays, again, let's remember the time it was written, etc., tend to vary linearly with the logarithm of the number of possibilities. For example, adding one relay to a group doubles the number of possible states of the relays. It adds 1 to the base 2 logarithm of this number. Doubling the time roughly squares the number of possible messages, etc. So he talks about, in a sense, as far as I get it, if you have degrees of freedom, I'll talk as a physicist now, that a possible system could be in. The logarithm of those degrees of freedom is, in a sense, gives you a valuable measure. Actually, usually it's entropy, he will introduce later, but in this case, he's talking about information. So it's how many degrees of freedoms you have. Does it make sense what I said here?
Yeah. I think a very simple interpretation. He's talking about binary representation of the data. You have 1,000 possibilities, and you need a logarithm of 2 of 1,000 is about 10 bits to represent it, because you have 1,024 options of all the combination of 10 bits. For me, I'm not thinking in the via degrees of freedom. I'm thinking about via the binary representation. So for me, just let's convert that into its binary representation.
Okay, cool. Probably better explanation, assuming it's binary. Then he continues, number 2, it is nearer to our intuitive feeling as to the proper measure. So at the beginning, he said, let's throw away meaning, but now he talks about intuitive feelings. Okay, cool. This is closely related to one, which I read previously, since we intuitively measures entities by linear comparison with common standards. One feels, for example, that two punch cards should have twice the capacity of one for information storage. So similar to what you said, Mike, right? And two identical channels, twice the capacity of one from transmitting information.
Yeah.
So assuming everything is binary, right? So you add one, you get two extra options.
Summing the bits. You're just summing the number of bits.
Yeah. Number three, the third reason, it's mathematically more suitable. Many of the limiting operations are simple in terms of the logarithm, but would require clumsy restatements in terms of the number of possibilities. So here it's like a pragmatic reason. It works.
Yeah, and actually, then I was reading this sentence, I was thinking about machine learning. I was thinking about log likelihood. Yeah, all the stuff we are doing in machine learning is not a likelihood. It is a log likelihood. Why it is log likelihood? Because we don't like multiply stuff, and you will easily get to underflow. We like summing stuff, and to sum stuff, you need to take a logarithm and invoke it on the multiplication. So for me, it is very intuitive.
By the way, I want to say that again, I think we said it before in one of the episodes, but you see how Shannon and other authors of his era are justifying everything that they do, trying to explain everything that they do. I don't see it in recent papers. I really don't. They don't say, if you can scroll up a bit, he's saying here, yeah, that's it. The logarithmic measure is more convenient for various reasons. And then he lists the reasons that he thinks is more convenient. Yeah, he's trying to convince the reader. That's unusual at this time, I think.
Yeah, sure.
And still he managed to do like 4 PhDs in this paper.
Yes, at the very least.
Okay, here he says that we can choose a different base to the logarithm, right? So we have infinite degrees of freedom. Which base we're going to choose? He says if it's the base 2, so it's binary, and the measure become bits, and it was suggested by Tukey. Then he says if the base is 10, they're called decimal digits. And near, if the base is the natural LAN, so how they are called?
It's called the kick to the nuts.
What is the name of the log 10? Natural algorithm? What is natural name?
No, natural logarithm is ln.
It's the LAN. It's the natural logarithm.
Natural logarithm is base e logarithm.
Yeah, base e.
Forgot it.
Yeah.
Then for the listeners, there's a schematic diagram of a general communication system, and it's easy. I'll explain to you. So on the left, there's the information source. So think about like blocks. It's connected to a transmitter. It sends a message to a transmitter. Then the transmitter makes an actual signal that goes on a channel. And there's the receiver that's, I think, gets the signal, transforms it to some message that goes to the destination. And on the channel also there's added noise. It's called source of noise. So we have like 5 blocks. And he says that's a general communication system, a diagram. Nir, does it make sense? We still use the same concepts today?
Yeah, still use the same concepts. We just know how to draw it more nicely.
You didn't like it?
Oh, this is fine. I mean, this is it's explaining everything. But these days we use Lucy charts or something like that, and you have these symbols inside, and This will not fly in a modern classroom now.
You know, when I'm looking at it, I can't help myself, but I'm thinking about variational autoencoder. If you then you look at it and think about information source as your very large data set of pictures of images, and then a transmitter as your encoder, and then just like you are doing in a variational autoencoder, you are adding some noise, and then you are trying to decode your signal, and you're trying to reconstruct your initial signal, your input. It is not it is a bit different concept, because in the encoder of the variational autoencoder, you are trying to estimate the expectation and the variance of the latent representation, but still, when they're looking at it, and I just can't help but thinking about it, because you know that these are very basic mathematical structures, and they are so simple, they are so similar that you know, I don't even know how they are correlated, but they really look very similar for me. At least for me.
Really interesting. I really liked it. And it dovetails in what you said previously, that you think a lot about the connection between compression and, in a sense, deep learning, or good representations of that data. And here he talks about how the transmitter should actually encode the signals, which is the data, so that it will actually go inside the channel that transmits the messages.
Right. We have an encoder and decoder here. This is a diagram of encoded decoder. It's not resembling. It is encoded decoder.
Yes.
The transmitter is encoding the information source, and he gives examples later. And the receiver is decoding the information source. That's it. So it is an encoder decoder system. We just didn't call it like a autoencoder back then.
But you know, the only difference is the noise source. Here you don't have any influence on the noise. In the variational autoencoder, you are just sampling from the random standard noise. It is a bit different.
Right. I'm not talking about specifically variational. Even a simple autoencoder, the data has noise in it. It doesn't matter if it's added in the channel or it's added before that when we take the picture of the image.
Really? You're right. It is just the noise autoencoder. I'm always complicating stuff, you know.
It's a simple autoencoder. What's drawn here, and it's the equivalence that you made is great. But I also think about it is like when I read it, I thought about simple neural network. There is an information source, which is the image, the audio, the text, whatever, right? And there is the encoding. Is it this class or this class or this class? Just grinding it down to a one-hot representation. That's encoding.
Yeah, very interesting. It's amazing how stuff in the machine learning and communication information theory is similar one to another. Just amazing.
Yes.
Cool. I really like this discussion. So I'll continue. So assuming you imagined or you see the schematic diagram, he's saying by a communication system, we will mean a system of the type indicated. It consists of essentially 5 parts. So now he describes the parts: an information source, which produces a message or sequence of messages to be communicated to the receiving terminal. Then he talks about different types, and we can move on of which messages could be sent, discrete, continuous, etc. Then he says there's a transmitter, which operates on the message in some way to produce a signal suitable for transmission over the channel. Then there's the channel itself, is merely the medium used to transmit the signal from transmitter to receiver. It may be a pair of wires, a coaxial cable, band of radio frequencies, a beam of light, etc. A neural network. No, just kidding. Number 4, the receiver ordinarily performs the inverse operation that's done by transmitter. So it's like encoder decoder, as we said, reconstructing the message from the signal. And at the end, the destination is a person or a thing for whom the message is intended. So it's now nice that it's inclusive. You know, it's not just a person, it could be any entity out there, a thing. Okay. Let's see. We wish to consider certain general problems involving communication systems. So again, we're still at the introduction. To do this, it is first necessary to present the various elements involved as mathematical entities. So now he's trying to formalize, right? You want to take this problem that of communication and trying to use math to formalize it, as I said. Okay. Suitably idealized form their physical counterparts. Wait just a second. Yes. We may roughly classify communication system into 3 categories: discrete, continuous, or mixed. Okay, so he said it already previously. Then he says that in this paper we'll be focused on discrete, but you can generalize the results to continuous ones. Here.
Daniel, I would like to ask Nir about the modern communication systems. Are modern communication system mixed because they are getting bits and then they're converting them to continuous signals with some D to A machinery, and they are transmitting actually continuous signals. So how can you define the modern communication systems?
I guess you can simplify it and say everything is digital.
Okay.
Even the channel, you can approximate it as coefficients, right? You taught me that, Mike, in your course, right? We have a channel, a matrix, so we digitize everything. But in real life, it's an analog signal carried by the air, carried on the medium, and then reaching an antenna and sample, right? That's what we usually do. But it can be fully digital on the wire. It can be fully digital on a laser. We can digitize or modulate the laser beam. But in the end of the day, it's a mixed. It's always some sort of a mixed representation, because the digitation is happening only in computers, so to speak, right?
Yes.
So before and after, it's always analog, carried in a medium.
Yes. Okay.
So we get to part number 1, discrete noiseless systems. So it's foreshadowing. In the future we'll get noise. Now there's no noise. We're in a nice, more simple world or a simple problem. Let's see. Okay, so he described a teletype and telegraphy system, so we won't go into it, because again, it goes dash and how to send the messages. It's less relevant, but he says, in the teletype case, where all the symbols are the same duration, and any sequence of the 32 symbols is allowed, the answer is easy. Okay, I'm not sure what happened here, but he says each symbol represents 5 bits of information. Okay, because there's 32 symbols, so you need 5 bits of information to represent them. And he says if the system transmits n symbols per second, it is natural to say that the channel has a capacity of 5n bits per second. It does not mean that the teletype channel will always be transmitted information at this rate. This is the maximum possible rate, and whether or not the actual rate reaches this maximum depends on the source information which feeds the channel, as we'll see later. And now it comes to a definition. In the more general case, with different lengths of symbols and constraints on the allowed sequences, let's say English, we have a finite number of words, we make the following definition. The capacity C, capital C, of a discrete channel is given by, and it's log of n as a function of t, which is the number of allowed signals of duration t. So think about log of the number of allowed signals divided by their duration, and we take the limit of the duration to infinity. Okay, let's see if there's some kind of intuition that or explanation he gives to why he defined it like that.
You know, I think it is quite a natural definition. You are just taking the number of signals in a very large time period, and you normalize it by this period length. I think it's quite natural to define channel capacity in this way. As a former mathematician, I'm only wondering, you know, and then you define some limit, you need to somehow to guarantee that this limit exists. And I hope in the most cases, in most practical cases, this limit exists, but from the pure mathematical point of view, it is an interesting question.
Yeah.
What happens if it is not?
So my response is we agreed already previously, or at least he convinced us that log is a useful tool. So now we have n allowed sequences.
Yeah.
So log of those allowed sequences somehow are equivalent to the capacity. But I don't understand why the limit, like why not just
This is
log
like,
of, so I'm missing something.
yeah, this is like, okay, think about it like that. Let's say we want to characterize empirically what's the bit error rate of a channel. So we transmit million bits, and then we count how many bits flipped, right?
Assuming
So,
we know
like,
what we sent.
Yeah, assuming we know what you sent, we sent. So let's say we counted 3. So we have 3 divided by million, which is approximation for the probability of the error, right? When will it be? When will it be the actual? When this relative frequency will be the actual probability of error? When n is going to infinity.
I get your explanation.
It's the same as this. He's normalizing it by the duration and taking the duration to infinity. So it's like infinite amount of messages. Let's see how many bits in average we have for a message. That's what we have here.
I don't get, because the lim is on the t, so it's not taking the number of messages to infinity, which is n. It's taking the duration to infinity.
Right.
That's what I don't understand.
The duration of each message is taken to infinity.
Yeah.
Which is like counting how many. The logarithm of this is how many bits. Okay, each message contains. The logarithm, so he's counting in average the relative frequency of bits extended to infinity. Kind of like we're counting probabilities in relative frequencies.
Yeah, okay.
That's how I understand it.
The frequentist definition of probability I get here. So in a sense, the channel capacity is like how much, again, similar to how much capacity it can encode, like when you say when you hear capacity,
how many bits per second can we transmit? That's it.
Can we transmit on this medium?
Yeah.
You know, it is for me also. I'm not sure it will help you, Daniel, to comprehend this, but for me, it just reminds the law of large numbers. You know, if you are building a sum of a very large amount of random variables which are distributed in the same manner, then you are taking the sum and dividing it by n, and then n tends to infinity, it converts to the expectation. And here is the same. You are taking a very large interval, and then you are computing how many bits you are capable of transmitting over this very large period, and then you are normalizing it by the period length. So for me, it is a kind of some continuous law of large numbers.
Okay, cool. So we got two intuitions. I hope that helps. I think it helped me in a sense. And now move on. He gives an example, a specific one. We won't go in it. We'll go to the next chapter, which is the discrete source of information. Okay, so we got the channel capacity. And now we're going to the source. that like makes them those symbols or those loud. I forgot. Not what was n.
And was the length of the
sequences. Yeah, n was the sequences. Okay, so now the source that makes them. He says we have seen that under very general conditions, the logarithm of the number of possible signals in a discrete channel increases linearly with time. The capacity to transmit information can be specified by giving this rate of increase, the number of bits per second required to specify the particular signal used. So I think when he says that it increases linearly in time, that's why we can use log. I didn't get what he said here.
I think it is one more explanation why logarithm is a proper measure for the channel capacity, because we are talking about number of bits in the binary representation of the information. So I think he's talking about it, but this paragraph is not entirely clear for me, I admit.
Yeah, that's why I think I marked it, so I can ask you, but let's continue. Probably you'll explain more. We now consider the information source. Okay, so yeah, he was talking about the channel capacity that we define. Now we're going to talk about the information source. How is an information source to be described mathematically? And how much information in bits per second is produced in a given source? The main point at issue is the effect of statistical knowledge about the source in reducing the required capacity of the channel by the use of proper encoding of the information. Okay, so it says if there's source that makes various symbols, that if we can encode them properly, then maybe we can utilize later the channel that has a specific capacity that we defined previously. That's how I got it.
Yeah, I think I have very simple case to explain it. Imagine you have your channel and the probability of 0 is 0.999 and the probability of 1 is 0.001. Instead of transmitting all these zeros, as the probability of 0 is very high, you'd better transmit 0 and the number of consecutive zeros and only then 1. And in this way, over the same channel, you can transmit much more information than if you're transmitting the signal as is. He's talking about this kind of encoding, I guess.
Yeah. He's actually in a formalized manner. He's talking about the maximum. He will define it later, like entropy, but he is talking about the maximum rate of transmission the channel can absorb. And this is just one encoding. He says, but he's basically saying there is an encoding scheme. I don't know what it is, maybe, that will allow us to get to the capacity of the channel. Okay,
Yes.
but an example is what you said, which is I think what we do with videos these days, and we're transmitting videos real time and stuff like that, right? If nothing changes from frame to frame, we just keep we just keep 1 bit for it or something like that.
Yeah, I think he actually gives an example here where he says in English the letter E occurs more frequently than Q, the sequence TH more frequently than XP, etc. The existence of this structure allows one to make saving in time or channel capacity by properly encoding the message sequences into signal sequences.
Right.
So he talks about the encoder, right? So he says like English is the messages, the sequences that we can send, and then there's an encoder that encodes them into signal, he calls it sequences.
By the way, here we have a very similar analogy with our deep learning. Instead of, for example, if you have a very large database of images, say you have 1 billion of images, then your users are trying to find some image which resembles the characteristics they give you. So you're not going to compare the representation of these features provided by the user with the images themselves. You're going to find some representations or some embeddings of these pictures or this image
Yeah.
by your neural net. So this encoding idea is very natural in the deep learning and machine learning as well.
Okay,
Yeah.
I like that you always see the connection to what we do, because I feel like I'm trying to understand what I'm reading, and I don't even can think about like meta, how it's related to other stuff. So it's cool that you have those insights.